Hello students and welcome to the molecular orbital theory. This will be the last theory that we will talk about when it comes to bonding, and it is the most conclusive one. The theory again came from a behavior of a molecule, and that behavior did not agree with the valence atomic orbital theory or the hybridization theory. So that molecule is oxygen. Oxygen turned out to be paramagnetic when we put it under the influence of a magnetic field. However, if we look at the hybridization model or the bonding model, it looks that oxygen has all electrons paired, whether they are paired in covalent bonds or paired as lone pairs. So the fact that it is behaving as paramagnetic does not really agree with the hybridization bonding theory or any other theory for that matter. It should be diamagnetic if anything, but we cannot say no to what we have seen. The observations are more honest than anything. Experiments have shown that oxygen is paramagnetic. So that led us to think about another theory to explain bonding, which is the molecular orbital theory. The states here that bonds are formed from molecular orbitals, which means those orbitals are not really there unless I make the molecule. They belong to the molecule and did not belong to the atoms making the molecule originally. So the overlap of two atomic orbitals will lead to the formation of two molecular orbitals. We're going to call one of them bonding and the other one anti-bonding molecular orbital. So every atom has atomic orbitals. When they are going to get together, then they are going to form what we call molecular orbital. And every two atomic orbitals will give two molecular orbitals. So here is an example. The two hydrogen atoms making a hydrogen molecule. Every hydrogen atom comes with its own atomic orbital, right? But when they bond, when they make the molecule, these two atomic orbitals are going to make a new molecular orbital. So these are no longer existing when they make the molecule. Rather, I have two new orbitals. One is lower in energy than the original atomic orbital, and that is what we call the bonding. And one is higher in energy than the original atomic orbitals, and that's what we call the anti-bonding. Okay? Now, when you make the molecule, every hydrogen atom had one valence electrons, right? So now when you make the molecule, we fill orbitals in lower energy first. And since I have two molecular orbitals now, remember these no longer exist, you fill the lower energy first, so the two electrons are going to go into the lower energy one or the bonding one, which is called here sigma. So this is a sigma orbital, and the anti-bonding is called sigma star. And if we put electrons in lower energy, that's stable. That means we are making a bond. If we start to put electrons in higher energy, that is unstable, and that will be breaking a bond. Now, if you want to look at it in a picture-wise to see the electron density, think of the orbitals as electronic waves, and we can add waves in two ways. In a constructive way, it means they're going to add up and create an electron density between the two nuclei, and that is bonding. Or they can also add in a destructive way, which they will cancel each other, and between the nuclei I have no overlap, or what I call a node. The bonding molecular orbital, as I have mentioned, is lower in energy and greater stability than the atomic orbitals it came from. The anti-bonding molecular orbital, it's higher in energy and lower stability than the atomic orbitals it came from. Now, also p orbitals can form two molecular orbitals. So like you just saw that the s orbitals formed sigma and sigma star. P orbitals can also form sigma and sigma star. This sigma though came from B, so I'm going to call it sigma 2p, and if it came from the specific 2p, that's why it's called sigma 2p. And then the other one will be sigma star. And the way we are looking at it, look at the pink orbitals here. You have two p orbitals that they can combine together. If this is a phase, so this is a plus with a plus, minus, minus, they can combine together in a constructive way in which I'm going to have the density between two nuclei to give me a sigma bond, or they can add in an opposite phases, which means the plus minus will get together and that will cancel out and create a node and make it an anti-bonding molecular orbital. They also, so p orbitals can make sigma and sigma star, and they can also make pi and pi star, right? Because we know there is a pi bond too. And they can come together again in a constructive way. So if there are phases, it will look something like that. The plus can come with a plus and the minus come to the minus, which will be added in a constructive way to give me a pi molecular orbital. Or if I add them in opposite phases like negative plus plus negative, that will create here a node. There will be no electron density overlap, and that is a pi star. And again, the p orbitals, as we have seen, can make 2 pi. So if px can do it, and also py on the perpendicular plane can do the exact same thing. Now, let's look at the molecular orbital configuration. Number of molecular orbital will always be equal to the number of atomic orbitals combined. Meaning, if 2 atomic orbitals are combining, they're going to make 2 molecular orbitals. If 4 are combining, they're going to make 4, and so on. The more stable the bonding molecular orbital, the less stable the corresponding anti-bonding molecular orbital. So let me show you this as... So atomic orbital can come together and they can make one bonding molecular orbital and another anti-bonding. Sometimes they can come like this and they make a way more stable bonding molecular orbital, but that means that the anti-bonding is also very unstable. We fill the molecular orbitals from low to high energy, which is always the case when we fill electrons. Each molecular orbital can hold up to 2 electrons with opposite spin, the exact same way we thought about configuration before. We use Hund's rule when molecular orbitals as the same energy, so we do not pair unless we have to. The number of electrons in molecular orbitals equal the sum of all electrons in the bonding atoms. So let's see, what does that mean? Also, the molecular orbital can allow us to calculate something we call the bond order. I have spoken about bond order briefly when I talked about resonance in the past chapters. So a bond order of 1 means I am looking at a single bond. A bond order of 2 means I am looking at a double bond. A bond orders of 3 means I'm looking at a triple bond. Now, sometimes I can have a bond order of 1.5. What does that mean? It means that this bond is stronger than a single but weaker than a double. Or lengthwise, this bond is longer than a single bond yet shorter. It's shorter than a single bond yet longer than a double bond, and so on. So here is a molecule, hydrogen 2+. There are 2 hydrogen atoms. Each one is with 1 s. The 2 molecular orbitals I am interested in filling as the sigma and the sigma star. In order to know what is the hydrogen 2+ look like bonding-wise, I need to calculate the number of valence electrons. I have 2 hydrogens, so this is 2 times 1 electron, and I have 1 plus charge, so I'm going to subtract 1 electron. 2 minus 1, 1 electron. So that means I'm going to have, these are the molecular orbitals I'm filling. I'm filling the lower energy first, and I have 1 to fill. after I fill my molecular orbital, I can calculate something that we call bond order. So what is a bond order? Let's see. A bond order is calculated by half number of electrons in bonding molecular orbitals minus the number of electrons in the anti-bonding molecular orbitals. Meaning, it is half how many electrons, here are the orbitals again. This is bonding and this here is bonding and this one is anti-bonding. How many electrons in the bonding? 1. Minus how many electrons in the anti-bonding? 0. So half times 1 equal 1/2. So the bond order for H2 plus is a half. What does that mean? To have a single bond, the bond order has to be 1. Half means it is weaker than a single bond and longer in length than a single bond, because the longer the bond, the weaker it is, right? So that's what does that mean. So now I know that H2 plus is weaker and less stable molecule than H2, because H2 has a bond order of 1. I have one single bond, and I can prove it because if I have H2, if I'm looking at H2, then I'm going to have to put another electron here, and now my bond order will be half 2 minus 0 equals 1. So that means one single bond for H2, half for H2 plus. Here is lithium 2. If I want to examine the stability of Li2 as a molecule, I can use the molecular orbital theory to examine any molecule that I want. So lithium has the configuration of 1s2, 2s1, 1s2, 2s1. Now, 2 electrons in 1s and another 2 electrons in the other 1s, so that's give you 4, which means you're going to fill these two first, and they will cancel out, right? Because it will be like half 2 minus 2, that is 0. These cancel out. And honestly, I really don't care about this. Why? Because this is the valence. The valence is the only thing I need for bonding. Anything below the valence will give you 0, will cancel out, because you're going to have to fill it all. So what I calculate the bond order from is really the valence. So now I have, in the 2s I have 1 electron for lithium, and in the 2s here I have 1 electron. So which means I'm going to have 2 electrons coming here. Now if I'm calculating the bond order, it will be 2 in the bonding minus 0 in the anti-bonding, and that will be 1. So Li2 will have a bonding equivalent to one single bond. Now let's practice. In order to, the molecular orbital theory might be difficult as a theory in concept, but the application is really straightforward and easy. In the application, you're going to draw the molecular orbital energy diagram, which is something I will always provide to you in quizzes and exam. You're going to write the molecular orbital configuration, just following the rule, lowest energy first, and we don't pair unless we have to. We predict the bond order, and we can also predict the magnetic property. So we have 3 molecules to look at, and I'm going to practice with you all this information about each one of them. The first one is B2, then BC, then C2 minus. So the way I do this, the first thing, this is a very common question in exams, right? So in the exam, guys, we are going to provide this for you, okay? Again, I don't look at anything below the valence, so that doesn't matter. They're going to cancel out and give me 0 anyways. So in the exam, I will give you this one, and it will look something like this. So let me show you. It will be like, I'm going to give you sigma. I'm going to give you sigma star, and I'm going to say this is sigma 2s. This is sigma star 2s. And then I'm going to give you pi, 2p, 2p, and then will be a sigma 2p, and then there will be pi star 2p, 2p, and then I'm going to give you sigma star 2p. So this diagram will be given to you. They are already arranged in energy going, let's go back, energy going up this way, so you know how to fill, okay? So the first thing you're going to do is to calculate valence of electrons. In B2, I have 2 borons. Each boron has 3 valence electrons, so this is total of 6 valence electrons. BC, boron has 3 valence electrons and carbon has 4 valence electrons, so together that will be 7 electrons I am dealing with. C2 minus, every carbon has 4 valence electrons and a negative charge, so that will be 4 plus 4, 8, and plus 1, that is 9 valence electrons. And I'm going to add to that, I'm going to also put O2, and O2 will be 6 and 6, 12 electrons. And I'm also going to put, let's try to practice more. Let's put also nitrogen, which is 5, 5, 10 electrons. And lastly, let's put fluorine, which is 7, 7, that is 14 electrons. Okay? So how do we go around this? And the first thing you will do, this is a very typical questions in exam. I can give you a bunch of diatomic molecules. I will tell you using the molecular orbital theory, tell me which one has the strongest bond. How do I know that? Strongest bonds mean the highest bond order. Which one has the longest bond? Longest bonds means the lowest bond order, and so on. Now, I'm going to show you, I will start, when I have a bunch of molecules, I will pick the lowest total number of valence electrons, in this case is 6. So I'm going to start filling the 6 electrons. So I'm going to say 1, 2, 3, 4, 5, and 6. Oh, I have unpaired electrons. So what does that mean? That this is paramagnetic. Can I calculate the bond order? Let's do that. Let's do that. That will be half. How many electrons in bonding? 1, 2, 3, and 4. I have 4. Minus how many electrons in anti-bonding? 2. Half 2 equals 1. So the bond order for B2 equals 1. It's paramagnetic with, I'm going to put the bond order here. The bond order here is 1. Okay. After 6 is 7. So 7 means I already have filled 6. So let's fill 7. Oh, it's still, I have 1 unpaired electron. So that's still paramagnetic. And the bond order now, I added an electron to the bonding. So now I have 5 minus 2, which is 3, divided by 2, that's 1.5. So the bond order here is 1.5. This is a stronger bond than B2. Let's do 9. So after 7, I have 9. I just did 7. So 8, right? That's 8. And here is 9. Oh, there is 1 electron that's unpaired. So that is paramagnetic. Okay. And now let's calculate what I have. So I added 2 electrons and I added both of them to bonding. So now I have 7 minus 2, that is 5. 5 divided by 2, that is 2.5. After 9 comes 10. Oh, for this one here, all of them are paired. So this molecule is diamagnetic, and now I added 1 electron here. So I have 8 minus 2, 6 divided by 2 equals 3. So the bond order here is 3. And does that agree with what we know about nitrogen? Nitrogen has triple bond, so the bond order is indeed 3. Now I have 12 for oxygen. So I'm going to have 1 and 2. And what I did here, look at that. I have unpaired electrons. So now the molecular orbital theory assured me that yes, indeed, oxygen is paramagnetic. And I added 2 electrons to the anti-bonding. So now this will be -4. 8 minus 4, 4 divided by 2 equals 2. The bond order is 2. And this is exactly what we know about oxygen. It is a double bond. Lastly, we can do fluorine. So this is 12, 13, 14. And that is diamagnetic. All of them are paired. And that will be 8 minus 6. That is 2 divided by 1/2. That is 1. And the bond order here is 1. And that's indeed what we know about the fluorine. It is a single bond. So the molecular orbital theory is indeed a very powerful tool in determining all the properties of the molecule. So please try to practice as much as you can about applying the molecular orbital theory to diatomic molecule. All of the atoms, by the way, has to be coming from period 2. So in reality, we are, actually, you are not responsible to know. The last slide that I just shown you guys, this is just extra information you are not really required to know for this class. This is all what you need to know about the molecular orbital theory. Thank you for your attention, and I will see you in the next chapter.